In this section, we discussed the Fermi level as the thermodynamic potential that can drive electrochemical reactions from one material to another. We discussed how different metals have different Fermi levels that could be measured from the bottoms of their bands or to a vacuum level just outside the metal measured by the work function. If the two vacuum levels are at the same overall potential, then the electrons with higher Fermi level or lower work function would reduce their energy by moving to the metal with lower Fermi level or higher work function. So when two metals are placed into contact with one another, electrons will move from one material to the other to create a charged interfacial layer. This charged layer creates an electrostatic potential difference between one metal and the other to the point where the Fermi levels will then become the same. The hydrostatic potential energy of water in two different containers can be used as an analogy. When the two containers are connected, the water will move from one container to the other to establish the same hydrostatic potential energy equivalent to the Fermi level in the two containers. The Fermi level is also known as the electrochemical potential because it represents the free energy per electron in a material. The electrochemical potential or Fermi level of a material can be changed due to the internal electric potential, but it can also be changed due to an external electric potential. In equilibrium, the internal electric potential difference is given by the work function difference between the two metals. The contact potentials produce no current because if made into a closed loop, the contact potentials would oppose each other. For the same reason, no electric potential would be measured by a voltmeter placed in one of the wires that makes a closed circuit. Electrons in a material can also be driven by a temperature difference. This is called the Seebeck effect. Generally, hot particles move faster than cold particles, such that when a material is placed in a temperature difference, the hot particles will diffuse faster than the cold particles, producing a net diffusion from hot to cold. This net diffusion leads to a buildup of charged particles at the cold end. This is similar to the evaporation of water at a hot end and condensation at the cold. In the case of electrons, this electrostatic buildup leads to a potential difference that we can measure as a voltage. The voltage produced is proportional to the temperature difference, and the proportionality constant is a material property known as the Seebeck coefficient. The sign of the Seebeck coefficient tells us the effective charge of the charge carrier, where for electrons as charge carriers we would normally expect a negative Seebeck coefficient. Later, we will see examples where the dominant charge carriers act like they have positive charge and have positive Seebeck coefficient. We can't measure the Seebeck coefficient of a metal using probes of the same metal because the same Seebeck voltage would be created in our probe metal as the metal we were measuring. If we make a circuit of two different metals with junctions at two different temperatures, there will be a net Seebeck voltage we can measure with a voltmeter. The voltage we measure will be due to the difference in Seebeck coefficient between the two metals. The Seebeck effect is the basis behind the thermocouple used for temperature measurement. The voltage measured in the voltmeter is due to the temperature of the sample, where there's a junction between two different types of metals, and a junction at a reference temperature, often an ice bath or an internal reference in the meter itself. Typical thermocouple materials are either nickel-based materials for low temperature operation or platinum materials for high temperature operation in air. The Seebeck coefficient of typical thermocouple materials is on the order of 20 microvolts per Kelvin and can be positive, which we call p-type, or negative, which we call n-type. Because the Seebeck voltage that we measure depends on the difference in Seebeck coefficient between two metals, we typically pick materials with large Seebeck coefficient differences, often one p-type and one n-type. The Seebeck effect can also be used to create electric power from heat, such as used by NASA in their deep space probes. Voyager, for example, has been operating for over 40 years using radioisotope heat source that is converted to electricity using a thermoelectric. The newest rovers on Mars also use radioisotope-based thermoelectric power. If we operate a thermoelectric in reverse, we produce a Peltier cooler, which has no environmentally harmful refrigerant gases. These can be used to make small refrigerators or distributed heating and cooling systems in electric vehicles.